All right, so the last couple um, sections, videos have been about radioactive decay and then half-life. Okay, and when we talked about radioactive decay, we talked about alpha and beta decay, but there was a third type, and that was called gamma rays. And gamma rays are just energy; they're not matter. So, like uh, alpha particles and beta particles are actually matter. They have they're either protons and neutrons or electrons. Okay. Um, Gamma rays are not. Gamma rays are pure energy. They're not matter. Okay. Remember, matter had to have mass and volume, which means it has to be made of protons, neutrons, and electrons. But gamma rays are not. They're pure energy. Okay. So we're going to talk about electromagnetic radiation here, which is just energy. But specifically, we're going to talk about high energy electromagnetic radiation as part of this, because during radioactive decays, gamma rays are very, very high energy type of electromagnetic radiation. Okay, so electromagnetic radiation, it's simply light. Okay, so we deal typically with visible light, but there's a whole bunch of different, but visible light is only one part of what's known as the electromagnetic spectrum. Okay, and light is simply energy. It's a way for energy to travel from one place to another place. Okay, so we can imagine that the light in the sun, the energy that's produced by the sun, travels as electromagnetic radiation through space and gets to Earth. Some of it gets to Earth, very little of it, but some of it gets to Earth and allows us to exist, provides energy that heats the Earth, keeps us at a temperature that supports life, allows plants to grow, and things like that. Okay, but if we can look at this little chart here, we can see that in the full electromagnetic energy spectrum, or electromagnetic radiation spectrum, the visible light, the stuff that we see with our eyes, the color, is a very small portion of it. And some of the rest of this we've probably heard of, and maybe all of it. At some point in time you've heard of the rest of it, but we're going to discuss a little bit more. Okay, so it's called electromagnetic radiation because it's got two pieces to it. It's got an electronic piece and a magnetic piece. We don't care too much about that in this class, but those two pieces allow it to interact with matter. So like when you go outside and the sun's out, you can feel the sun's warmth. You feel the sun's warmth because the electromagnetic radiation, or the light, interacts with the matter that makes you up and causes your body to warm up or heat up. It gets absorbed by your body. Okay, so if we look at the electromagnetic spectrum, there's different parts of it. There's gamma rays, which are really high energy electromagnetic radiation. X-ray is a part of it. That's also very high energy radiation. Ultraviolet, visible, infrared, microwave, and radio. Okay, so radio waves are electromagnetic radiation, but it's really low energy electromagnetic radiation. Microwave is used for a lot of things, for communication, but also we have microwaves in our house that produce microwaves that heat our food, and so on. Okay, the sun produces all of this, mainly X-rays actually, but also some gamma rays, obviously some ultraviolet and visible. Typically we consider this higher end stuff, the higher energy stuff, the ultraviolet, the X-ray, and the gamma rays, to be damaging to humans, to be damaging to our skin, and to other parts of our bodies. Damaging meaning that it changes your cells and causes defects that can cause cancer and things like that. Okay, so Single packets of electromagnetic radiation are called photons. Photons are just packets of energy that travel from one place to another. Okay, and those photons can be it can lie anywhere in the electromagnetic spectrum. Some photons are visible light. Some photons are gamma rays. Some photons are X-rays. Okay, but photons are just little packets of energy that are traveling through space. Now, typically we depict photons or light, electromagnetic radiation, as waves. Okay. In fact, the photons are not like moving in a wave-like fashion. They're not. They're moving in a straight line, but they have properties that are wave-like. We said it's got an electronic piece and a magnetic piece. Well, those pieces are wave-like. That's why we depict them as waves. Okay. So, as with any wave, we have a distance between peaks, and that's called the wavelength. The wavelength of a wave is the distance between two peaks or two troughs, but we'll do peaks. So it's basically how far the wave travels before it starts repeating the same pattern. Okay, so I just take two peaks, and between those two peaks is the wavelength. And wavelength is actually depicted by a lambda, which is a Greek letter L, and that's a lowercase lambda. Okay. Shorter wavelengths means that the photon is carrying more energy. Okay, so shorter wavelengths mean higher energy. Longer wavelengths, if the distance between two peaks or the distance that it takes for it to repeat itself are longer, then the photon is lower in energy. Okay, and we'll go back to the electromagnetic spectrum here in a second. And show you what that means. Alright, so doing that. So back to our electromagnetic spectrum. So the higher energy end of the electromagnetic spectrum has photons that have really short wavelengths, really high energy. Okay. On the other end, the lower energy end has photons that have really low energy, really long wavelengths. Okay. The gamma ray and X-ray end are going to be the higher energy end, and for the visible region, where visible light occurs, happens between 400 nanometers and 750 nanometers. That's wavelength. Okay, so the purple-blue end has shorter wavelengths. That means a photon that's carrying energy that's associated with blue light is going to be higher in energy than the photon that's carrying energy associated with red light. Okay, and the nanometers are simply what the wavelength associated with those photons is. So the visible spectrum occurs we typically consider it between 400 nanometers and 750 nanometers. Okay. Gamma rays and X-rays are known as ionizing radiation. So ionizing radiation means that when they hit matter, they can ionize the atoms in matter. Okay, ionizing means simply causing an electron to leave. Okay, so if you've got an atom and that atom is hit with X-rays, let's say, and those X-rays cause the atom to ionize, that means an electron leaves, and now we've got a positively charged atom. It's not an atom anymore, it's called an ion now because it's charged. Okay, so ionizing radiation causes electrons to leave whatever they're interacting with. So ionizing radiation causes electrons to leave. Okay, so we've learned that UV light is bad for us. And that's true, right? So UV light is it causes damage to skin cells, and therefore that damage can create cancerous cells. But there's also benefits of UV light, not just for plants, but for humans. When you go outside, your body uses UV light to produce vitamin D, which is essential for your life, your living. It's in fact said that you should have 15 to 20 minutes of direct sunlight to produce enough vitamin D for the day. So being outside in the sunlight is good in some senses, at least for limited amounts of times, because it allows your body to produce vitamin D. So again, we're in that situation where there's good and bad that come with most everything. UV light can do damage to you, and if you're outside too long without proper protection, you at some point will start causing your skin cells to convert to cancerous cells. That being said, you do need some sunlight. It's beneficial for you to produce vitamin D, and you need vitamin D. So there's this balance between a correct amount of stuff, in this case UV light, and too much.